Howdy folks, welcome back to CS 128 Honors. In today's lecture, we're going to be talking about threads and mutual exclusion in Rust. So this is our last lecture covering threads. This is sort of the other approach to sharing data between threads that we talked about. In the last two lectures, we talked about channels and sending messages between threads. That is the preferred way to do things in Rust. Today is going to be sort of another sort of overview of how to share data between threads, but ultimately you'll be using channels and message passing most of the time. Okay, that being said, so like I said, we're going to be covering more ways to share data between threads. So this is going to be a Mutex lock. So we're going to talk about what that looks like in Rust, and then go a little bit into atomic reference counts and just the general principles of atomicity, and actually introduce what that means and how it sort of comes into play in multi-threading. So these are all topics that you'll see sort of in advanced systems programming courses. If you end up taking CS 341 or CS 233, you'll learn about these a lot more in depth. So hopefully this lecture gives you just a brief look ahead to what you'll be learning when you take those classes. Okay, just a couple quick reminders. So Homework 10 was released last Tuesday. It's due on the 18th. And MP3 also released last Tuesday, due next Friday on the 21st. Okay. And keep an eye out next week for final project logistics. We'll be releasing a couple of videos and some documentation on what that's going to look like. And you'll have the remaining 8 weeks of the semester to work on your final projects. Okay, so let's talk about sending and sharing data between threads. So we said that we can share data by either passing messages or by sharing some memory, sharing some data structure between threads. And we said it's somewhat harder to do that. And so the entire lecture will be showing you why it's such a challenge and how to sort of get around that using some advanced Rust features. So the last two lectures, we covered passing messages between threads using the multiple producer, single consumer, the sender and receiver types. Today, we're going to be talking about how you can share data using what's known as a Mutex lock. So Mutex locks allow you to share memory by taking advantage of some sort of advanced features built into Rust's type system. And I'll be sort of pulling back the curtain and giving you a little bit of a look at what a mutex is and how that sort of ties into the ownership and borrowing model. Okay, so just generally, what are mutex locks? So mutex is an abbreviation for mutual exclusion. Mutual means just sort of held in common. You have some mutual data between threads that you want to share. Exclusion means you deny access. So when you put that together, you have this lock that allows only one thread to access some data at any given time. So if I have some piece of data I want to modify, only one thread can change that at one time, or even read that at one time. So just as a sort of general example, tying to the real world, let's say you have this panel of speakers at a conference, and you only want one person to speak at a time. So this is somewhat similar to the use case of a mutex. At a conference, you have a microphone, so only one person can be heard around the conference room at one time. Well, in this case, the microphone acts as a mutex. It allows one speaker to access access the audience's attention at a given time. Only one person can actually be heard throughout the room. So you're sort of denying access to the other speakers while one person is talking. Okay. So mutexes in Rust sort of come with this associated data. Mutexes are in essence a smart pointer. This is different than many other languages where a mutex is sort of protecting code, and I'll show you what that means. But a mutex is in essence a smart pointer. Similar to box, it contains some data. So if you want to access the data inside a mutex, you must, as a thread, you must first signal that you want to access that mutex's data. So you'll tell the mutex somehow that, I want to access this data, I want to request this lock that you have on the data. So this lock is a data structure that is part of the mutex, it identifies that a certain thread has access to some data at some point in time. So it keeps track of which thread currently has exclusive access to the data. We said a mutex lock, mutual exclusion, means only one thread can read or write a piece of data at a time. And so the lock keeps track of who has that exclusive access. This lock in Rust is also called a mutex guard. More on that in just a bit. Okay. And like I said, only one thread can hold a lock at a time. So a mutex is like a smart pointer in Rust. It guards the data it holds with this locking mechanism. This is different from many other languages like C and C++, where mutexes guard what are known as critical sections. Critical sections are these pieces of code that modify or read or update some shared piece of data. So rather than having a section of code you want to modify, mutexes in Rust protect data. So just like ownership, you can only have one owner of some data at a time. That critical section problem doesn't necessarily yield itself to solving that one ownership problem very well. So you have this mutex, you have this notion of mutex owning the data inside them. And so you can access the mutex, but the mutex itself owns the data. Okay, so like I was saying, a critical section is this piece of code that cannot be run by multiple threads at once because you have some data inside there. You have some shared resource that you want to protect, and you only want one person to access it at a time. So the rules of the critical section problem. So if you want to sort of access this shared data, you must first acquire the lock of the mutex. You must be the one thread that has exclusive access to this piece of shared data. Then you can sort of play with the data as you like. You can change it, read it, modify it, whatever. But when you're done, you must unlock the data so other threads can acquire the lock and also use the data. There are a lot of issues that arise when threads do not release the lock. So you'll have this thing called deadlock where your program is stuck because some thread owns or has owned this lock and is not releasing the lock, which is an issue. So the important bit is you acquire the lock when you want to use the shared data, and then you release the lock when you want other threads to start play with the data as well. Okay, so mutexes in Rust. You've seen this pattern before. You just say mutex new to create a new mutex and provide mutual exclusion to data. This is super similar to the box smart pointer in construction. You just say box new with your data inside. Mutex, just say mutex new. Okay, so this is where locking comes into play. If you want to modify the data that the mutex has, you want to be the exclusive. You want to have exclusive access to it. You need to acquire the lock. So mutex.lock attempts to lock this data, and unwrap gets you the mutex guard for that data. It gives you that mutual exclusion to allow you to modify that piece of data. So lock either attempts to acquire the mutex's lock, and if it is unable to acquire the lock, if another thread is currently holding that lock will block until the other thread releases that piece of data. So this is how the mutex lock only allows one thread to access that piece of data. You either get the lock if there are no threads reading, or you wait until all other threads have stopped trying to, or have released the lock, and then you try again to get that piece of data. Okay, so mutexes are automatically unlocked when this mutex guard goes out of scope. So you don't see this unlock call here because it's not necessary. Because of the rules of scope, when this mutex guard goes out of scope, well, your mutex, or you sort of lose access to the data inside the mutex, so other threads can access it. So we're sort of taking advantage of ownership and scope and just removing this extra overhead of calling unlock and removing the possibility that a thread does not unlock the data. So mutex.lock gets you this mutex guard, which gives you mutual exclusion to read or write the data inside our mutex. So you don't need to worry about unlocking mutexes in Rust because scope and ownership handles that for you. Okay, so let's get into a quick example. Let's say we have this shared data between threads, this just integer that we're going to increment throughout our program. So we've seen this pattern before. We create our mutable vector of thread join handles, spawn 10 threads, push each thread handle into our vector of handles, call join on each thread, and block until each thread is finished. And at the end, we'll sort of print out a result. The new syntax here is creating our mutex and getting the mutex lock. So what this ends up doing is saying we pass in this mutex into each thread, attempt to unlock the mutex, increment it by 1, and then this guard goes out of scope, and some other thread can try and lock the mutex again, or this thread can try and lock the mutex again, whatever it may be. But we have an issue. Remember, we said that only one thread can have ownership of some value. And when we say thread move, we're moving ownership. We're not cloning data. So we're sort of stuck here. We get this compiler error. This mutex is moved into the first thread, and it doesn't implement copy. It's not a primitive type. So we have this issue where we want to be able to share data between threads, but threads can only have only one thread can have ownership of this data. So there is a way around this. So we want this advanced type to allow us to share our mutex between threads. So there's this thing called the arc smart pointer. Stands for atomic reference count smart pointer. So what this does is it says, we have this piece of data we'd like to share. We want it to have multiple owners. So we're going to sort of play a little trick. Rather than sort of giving a reference to each thread, we're going to have a separate smart pointer. We're going to have 10 different smart pointers for 10 different threads, but all 10 smart pointers are going to reference the same piece of data. They're all going to reference our mutex. So what this does is it keeps a count of the number of references to the data inside the pointer. And only when the count is 0 will we drop that data. So if one arc goes out of scope, if it is dropped, it's not going to actually delete the data unless there are no more arcs. So this data is going to live as long as there is at least one smart pointer that references it. Don't worry too much about how this is implemented, how it works. The main takeaway from this lecture is if you want to use shared state, you have to use a mutex and an arc. And so this is what this lecture is sort of working towards. Okay, so I explained what reference count is. You have a count to the number of references to this data. What does atomic mean? So there's this notion where when you want to access or mutate some property, some data, and you want it to do atomic, this means that only one read or write operation can be performed at a time. So this sounds similar to a mutex. You only want one entity, one thread, to be able to perform an operation at a time. But we said we wanted an arc to wrap around a mutex, and we want to use a mutex to sort of control the arc. Well, we run into this sort of circular issue here. This is where you involve the hardware people. This is where you involve the ECE majors, the electrical engineering majors. Atomicity sort of comes down to hardware, and it's not truly the programmer's job, but there are ways around it. Anyways, atomicity is sort of this property that you want one thing to happen at a time, and we'll sort of point out why in a bit. So if you have a thread-safe count of the number of references, you have a mutex on the number of references, well, then this gives you a thread-safe pointer. Okay, so I just want to briefly go over what atomicity means. So in your CPU, when you want to modify this value, the CPU will do three things. It'll first load the value from memory, from RAM, into what's known as a register. And then your program will sort of operate on these registers to perform computations. Then your CPU is going to modify that value in the register, and finally store that value in the register back into memory. So you have 3 operations to just modify a single value. Okay, and from the last 3 lectures, we've been sort of reinforcing that there's no guarantee of thread execution order. So if you have 2 threads running at a time, you can't guarantee the order that they're operating. Okay, so let's consider this non-atomic sequence of events with 2 threads and some integer data. So we'll initialize our data to be 0, and we're going to be adding 1 to data from each thread. So in thread 1, we're going to load data into some register. This is an x86 register. Don't worry too much about what it is. So we load data into this register. Data is 0, or register is 0. Then we load data into register on thread 2. So same thing, different register, load data equals 0. Then we modify the register when we increment data by 1. So data in memory is still 0, but the register is now 1. Same thing on thread 2. Data is still 0 in memory, the register is now 1. And then we write the register back into memory on thread 1. So data is now equal to 1 in memory and in the register. But when we try to write data into the back into memory on thread 2, we're writing the value of the BX, that other register. So it just goes from data equals 1 to data equals 1, because we did not have this atomic sequence of events. So we said that there's no order or no guarantee of order between threads, so you can't really have atomicity when you have threads that are able to sort of compete with each other and override each other. If we had atomicity, what we'd see is we first performed all the operations of thread 1, so load, then increment, then write, and then all the operations of thread 2. So load thread 2, increment, and write. So atomicity means if you want to write some value, it happens sort of instantaneously in the eyes of your processor. So all of the operations for write happen at once, then all the operations of a separate write happen after. They're not interleaved. So we incremented data twice, but its value is only 1. Because our sequence of events is not atomic. Our integer does not have atomic operations performed on it. So let me just remove my camera. So with atomic operations, we want writes, operations that modify some data, to happen instantaneously. So any other readers or writers will always sort of see the correct value and have the correct value to work with throughout your code. So this is a super advanced feature of computer science. You'll learn much more when you take systems programming classes, computer architecture classes. Don't worry too much. This is just sort of an intro to sharing data between threads, and this is why sharing data is so tough in Rust, because of all of these sort of guarantees you have to give for memory safety. Okay, so we talked about the arc smart pointer. Here's how to use it. So as with all smart pointers, you have arc new and then the data inside. And when you want to sort of create another smart pointer, so you have 2 that point to the same internal piece of data, you call clone on that. So this is the sort of advanced features of Rust. When you call clone, you create a pointer, but you reference that same piece of data inside. So this is the notion of smart pointer. It's smart about what it does, and it allows you to sort of be tricky. So when you clone your arc, you create a separate structure, but they reference the same piece of data. And so what clone does is it increments the number of references to the data. So if you had 1 reference, now we get 2. And so what this allows you to do is sort of reuse that data, and once all of your clones, once all of your structures go out of scope, then the data is dropped. Okay, so you're going to pass the cloned pointer into your thread, so you can continue to reuse that or clone the original arc when passing other pieces of data into your threads. So how do we fix our example from before? It's super simple. You just wrap your mutex in an arc. Everything else is the same. You have your handles, you have your thread creation, thread joins, and at the end you can print that out. Arc is simply a wrapper that allows you to clone your mutex, or rather have cloned references to your mutex, so you can pass the mutex into multiple threads. So we create our arc, clone that piece of data. So each clone refers to mutex, but it's technically a separate structure. So we move the clone into our thread, try to get the lock on that, and unwrap and increment that one. Okay. So let's see how this looks in Rust. So same thing, we have an arc, we clone our arc, and we have this little loop that will sort of loop through, try and increment our lock, and go from there. And there we go. So we have this shared piece of data between threads. We have this shared integer, and we're able to sort of go through our threads. Each thread accesses that same piece of data, and at the end in our main thread, we can print that out. So super powerful tool, just a lot more overhead with an arc and a mutex to access that piece of data. Okay, so the big takeaway from today's lecture, if you want to sort of create some shared piece of data, you have an arc around it, call clone on that arc, and pass that arc into a mutex. Or sorry, rather, pass a mutex into that arc and pass that arc to your threads. All right, that's all, folks. Kind of short lecture today. This is the end of the core Rust content in CS 128 Honors. The next lectures will be sort of on advanced topics that will help you throughout your final projects. So no more Prairie Learn homeworks, but you will start to work on final projects in the next coming weeks. All right, take care.